In this lesson, we're going to learn about functions and about numbers. So functions is the way to teach the system, in a sense, to remember a piece of program, fragment, so that we can re-execute it with maybe different values for the identifiers. And numbers, well, we already used integers, but let me introduce another kind of number, which is a floating point number, and show you the difference between integers and floating point numbers. So with functions and numbers, then you'll be able to calculate and do much more sophisticated things. So let me here define a function, sqr, x. So sqr is the name, fun is the keyword that starts the function, and x is the argument. So the x is the identifier that will refer to the new variable each time you call the function. So this function has the body x times x. So this is the expression that will be executed whenever you call it. So let me call this one now. I do browse of square of 10. And this displays 100. And I do browse of square of 11. And this will display 121. So now we have, in some sense, taught the system a new ability, which is the ability to make squares of numbers. Okay, so that's the basic idea of functions. Let's now talk about numbers. To show that, let me show you another kind of call. Let's call square with another number. This is a number with a decimal point, 10.1. And the result is 102.01. So, in fact, 10.1 in this system is a very different number than 10. 10 is an integer, which is an exact number. 10.1 is called a floating point number, and in Oz the distinction is seen by the fact that it has a decimal point when you write it. So a floating point number is essentially an approximation to a real number, to a certain number of digits. In Oz it uses 64-bit internally, so it has around 15 digits. And the integers are exact within their range. So in the Mozart 2 system currently the integers are 64-bit, so that gives them up to 19-digit precision. So the integers are therefore exact, and the floating point numbers are approximate. Let me define a new function now that will take any 3-digit integer and return the sum of the digits. So for example, for 123, it will return 1 plus 2 plus 3. Let me call this sum digits. Let me make the argument be called n. And now I have to add the 3 digits, so I introduce a new function here which is called modulo. So n modulo 10 is the remainder after dividing n by 10. But then I need to get the next digit, so I do n, I divide it by 10, and that result I take the last digit, and the final one I do n div 100. There's a parenthesis missing, there we go. And this one will give me the sum of the digits of any 3-digit number. So for example, sum digits 1, 2, 3 returns 6. Sum digits 999 returns 27. 9 plus 9 plus 9. Notice there's the two functions here, mod and div. These two functions work only for integers. They stay within the world of exact computation with integers. Whereas if you want to work with floating point numbers, we cannot use mod and div. So for example, if I do 999 mod 10, this will give me the remainder after dividing by 10. This is 9. If I do 999 div 10, this will give me the integer division, which where I remove less, I drop the remainder. This gives me 99. Now this works only for integers. If I want to division on floating point numbers, I need to use another symbol, which is the slash. This is a floating division. This will give me the best approximation in the floating point number. Oops. Now I have an error here. Why do I have this error? Well, in fact, because I tried to use the division on integer numbers. I tried to use a floating division on integer numbers. The way to make it work is to add the decimal points, and then the result is 99.9. So in fact, the way it works is that there's two worlds. There's the world of exact calculation, in which the integers are living, and then there's the world of approximate calculation, where the system tries to find the best approximation to some real number. And these two worlds are separate. So mod and div live in the exact world, the slash lives in the approximate world, and if you're a clever student, you'll notice that the star here, the asterisk, which is the multiplication, actually works in both worlds. If you give it in integers, it'll return an integer. If you give it a floating point number, it'll return a floating point number. So we have these two worlds, integers and floats. So you might want to ask, how do we go from one world to the other? Each world is separate. There is no automatic conversion, so the system will never, behind your back, change a number from one world to the other. You have to do it yourself if you want to. So this is so that things will remain very simple and easy to reason about. There's no complicated rules about automatic translation. But if you want to go from one world to another, there are functions that let you do it. So for example, there is a function int2float, which takes any integer, such as 999, and tries to find the best floating point number. So this returns 999.0. And there's an opposite function called float2int, and if I give it a floating point number, it returns the integer that best approximates it. Now float2int will do a rounding. It will actually try to find the integer that is somehow closest to the float. So if I do float2int of 3.5, then it will say the closest one is actually 4. If I do float2int of 2.5, well then naively you might say this is going to return 3, but that would make a bias. That means that if for every time we have a number that ends in a decimal 5, we would round to the integer up. We're introducing a systematic increase, and that's wrong. So in fact, the floating point standard of current computers, the IEEE standard, states that you don't do this. What you really do is you round to the nearest even integer. So 2.5 is actually rounding to 2. And this is what float2int provides, and this gives you a correct, unbiased round operation.